Good morning, ladies and gentlemen. My name is Maxwell Arbiter from Group 59. Today we'll be evaluating question 5 from the given set of questions. Now this problem approaches simple harmonic movements, specifically an underdamped motion. Now underdamped harmonic motion and damped and critically damped motion plays an integral role in mathematics, engineering, physics, and a lot of real-world problems. So, to start off the question, the first part of the question talks about this solution here, yt. Now yt states 1 over 1 minus omega squared, and I'm just going to call that my omega constant throughout this problem, outside of cos of omega t minus cos t. We want to prove that this solves the differential equation y double prime plus y is equal to cos of omega t, with the initial conditions given here, both when y and y prime equals 0 at 0. So, to start off, we're going to evaluate the general solution via the auxiliary equation here. Now, the auxiliary equation states that a y with an nth prime follows m with an n component corresponding. Now, if we take y double prime plus y, given we have 2 primes here, we get m squared. Given we have 0 primes up here, that'll be plus 1. Now when we set this to 0, given that it is a general solution, we see that m squared equals minus 1, and the only number that, when squared, that equals minus 1 is the imaginary number, the square root of minus 1. So we see that m1 and m2 are plus and minus I respectively. Given the roots of the auxiliary equation are imaginary, the general solution takes the form as seen in Euler's identity, e to the alpha t outside of c1 cos beta t plus c2 sine beta t, where for all alpha and beta, alpha is given as the real component of the m value and beta is the imaginary component. Thus, when we see we have 1 lot of the imaginary unit and 0 lots of any real number, we see that the y general solution of t is equal to e to the 0 t outside of c1 cos t plus c2 sine t, and that's just going to equal this expression here as that goes to 1. As the general solution has been evaluated, evaluate the complementary solution, that is, evaluate y sub c. Assume y sub c takes the form y sub c of t is equal to a cos of omega t plus b sine omega t. Therefore, the derivative y prime sub c of t is equal to, if we differentiate this with respect to t, we get negative a sine omega t plus omega b omega t. And then the second derivative, y double prime sub c of t, is equal to the same thing, the derivative of this, which would give us negative omega squared a cos omega t minus omega squared b sine omega t. When substituted into the original differential equation, i.e. this one here, this reveals the coefficients of a and b, just arbitrary constants. Now we have our y double prime plus our y prime term is equal to cos of omega t. If we gather the like terms, let's say for a cos and b sine, we see when we're evaluating the coefficients, we see that a cos of omega t minus omega squared a cos omega t is equal to cos of omega t. When we factor the cos function out and then divide both sides by the cos of omega t, we see that a is equal to 1 over 1 minus omega squared, my omega constant. Now, if we evaluate the sine portion, given that there is no sine portion of this equation, we see that b must equal 0. Alright, let's keep going. Thus, the particular solution is equal to my omega constant outside of cos of omega t. As the final solution for the differential equation is a linear combination of all solutions, now we know that for any nth order differential equation, the general solution and the complementary solution give us y of t, there's no subscripts here because this is our actual function, y of t is equal to my omega constant outside of cos of omega t plus C1 cos plus C2 sine. Now with the initial conditions, when we substitute this into the original function and the derivative, which can be derived just from the rate of change of this function, we see that 0 is equal to, in the first initial condition, 0 is equal to my omega constant plus cos of 0 plus C1 cos 0, C2 sine 0. Now this goes to 0 and these both go to 1, which give us C1 is equal to minus 1 over 1 minus omega squared. So a negative my omega constant. Therefore, when we substitute into our second initial condition, we see that 0 equals, where 0 is equal to every point at t. Now given this is the only one that does not go to 0, as sine of 0 both go to 0, we see that C2 must in fact be equal to 0. Therefore, we get the general solution here, yg is equal to minus 1 over 1 minus omega squared outside of cos t. Thus the final solution, when we add them both together, and I'm just going to skip a step here and factor that omega constant out, we see that yt is equal to my omega constant outside of cos of omega t minus cos t, the exact solution we were looking for in the first portion of the question. Awesome. So now things get a little tricky, so I'm going to need you guys to follow along with me here. Part 2 of the question states we want to show that this expression here is equivalent to this one. Yt is equal to negative 2 over 1 minus omega squared outside of sine omega plus 1 over 2t sine omega minus 1 over 2t. Now to start, we know that these two expressions are obviously different. They contain different periodic functions. So we're going to need to complexify this. And I'm just going to start by addressing two trigonometric identities that will be used explicitly. That is Euler's identities, or a portion of them. So we're going to say cos for any angle theta is equal to 1/2 of e to the I theta plus e to the minus I theta. And the same thing with sine of the theta is equal to 1 over 2i outside of e to the I theta minus e to the minus I theta. And we're going to start this proof now. A lot of math involved here, guys. So we're saying, right to prove my omega constant outside of cos of omega t minus cos t is equivalent to negative 2. I've just put this out the front, and you'll see why in a second. 1 over omega, my omega constant, multiplied by minus 2 sine of omega plus 1 over 2t, multiplied by sine omega minus 1 over 2t. Now if we re-sub in these expressions here, except instead of sine functions, we're going to use Euler's identities, we see that I have my omega constant outside of 1/2 e to the I theta t, omega t, and that omega t just comes from, instead of saying theta, it'll be omega t as our angle, given it's a function, minus the same thing as this, 1/2 e to the it plus e to the minus it. And now we do the same thing for the sine expression. We see my omega constant multiplied by minus 2 given here, sine e to the I omega plus 1 over 2t minus e to the minus omega plus 1 over 2t. And we're going to take that, we're going to multiply that by the same thing, 1 over 2i to the power of, multiplied by e to the I to the power of omega minus 1 over 2t minus omega to the minus I omega minus 1 2t. Now given the omega constant, these two appear on both sides, we can simply cancel those out, as that is an arbitrary constant on both sides of the expression. So when we multiply these through, we're going to try and make this side, the right hand side, equal to the left side over here. So the first step is that we're going to need to simplify this expression. So given I have a 1 over 2i here and here, I'm going to factor those both out of the question and multiply them together, given that we have a term multiplied by a term, by a term, by a term. So we get 1 over 4i squared. Now that's simply just going to go to 1 over minus 4, given I squared equals minus 1. And we'll take that one straight out. So we get minus 2 over minus 4. Obviously, just a half. Still multiplied by my expressions for sign. Take that out the front, and we have 1/2 outside of the multiple. Now we go inside bracket, outside bracket, inside bracket, outside bracket. So we have e to the I omega plus 1 over 2t, and we're going to multiply that by the same thing but with a minus 1, plus this expression here, e to the I omega plus 1 over 2t, multiplied by minus e to the minus I omega minus 1 over 2t. We're going to add that to the same term there that we just talked about, except with a plus, multiplied by e to the I omega minus 1 2t. Now keep in mind, guys, that this is just basic expanding of brackets, except the terms inside might be a little trickier. Plus e to the I minus omega plus 1 over 2t, outside of minus e to the I omega minus 1t. And when we simplify these down, we get to this point here where we can add the exponents together, given that these are just an exponent law. Okay, so we have 1/2 of e, outside of e it, outside of omega plus 1 over 2 plus omega minus 1 over 2, minus e to the it, outside of the same thing, omega plus 1, omega plus 2, omega plus 1 over 2, minus omega minus 1 over 2. And that's the same thing, these follow straight through, so we can simplify this even further now. We can say that e to the it, outside of 2 omega over 2, minus e to the it, 2 over 2, minus e to the it minus 2 over 2, and e to the it minus 2 omega over 2. We cancel these fractions down. We see 1/2 of e to the it omega minus e to the it minus e to the minus it plus e to the minus it omega. Now I'm just going to rearrange that to get the like terms where we have omega, omega, regular, regular. And if I multiply that fraction through, and you'll see why now, I multiply that through, and then I'm just simply going to group them again in terms of like terms. And now I can refactor them out from these brackets where I have 1/2 e to the it omega plus e to the minus it omega minus 1/2 outside of e to the it minus e to the I minus it. Thus, this expression here is directly equivalent to that we started with, that we were trying to show. Thus, the expression is directly equal to that of the left-hand side. Thus, we conclude that the left-hand side is equal to the right-hand side, namely, our expression, this, is congruent to this. Thank you very much for watching today, guys. I hope you enjoyed.